go where I need to advance my slides. So, okay. So very good. Oh, that just okay. Down is forward. Okay, so just to be a little vague with my title, because I think a lot of times people say, "Oh yeah, it's high resolution." Well, what do you mean high resolution? And I'm coming from the Sentinel 5P, so Sentinel 5 precursor, so in the same Sentinel family, but very different measurements. So I think it'll be a nice comparison contrast with what we've seen from Sentinel 2 this morning. And all of the issues that were discussed in detail about the CDSE are also, and ZAR and formatting are all relevant for our data as well. So also feel free, if you have burning questions, I don't mind if you interrupt me or something's really unclear, just raise your hand and we'll discuss it. So I will be presenting again, so space-based spectrometry for measuring air quality and climate relevant species. And I will show you kind of our world and the things that we are measuring and how that compares and contrasts to land imager based things. So this is me. I've been working in the field since quite some time. I'm mostly based at KNMI once I finished my PhD in environmental research, but I have a meteorological background and I got to do a lot of air chemistry field work early on in my student career, extending into my professional career in the field, doing satellite validation campaign in the Central Valley of California, but I've also been to Southern Africa and all different places in the US, and the Netherlands has a great, excellent networked measurement site for many different types of trace gases in Cabal, in the center of the country. So I've worked on field campaigns there as well, and I really like the tension between understanding the algorithms and understanding the measurements that you need to make on the ground to do the ground truthing and validation for what the satellite sees. So why are satellites important for air quality and understanding that as a data set? As we've seen from meteorology, almost all the data is coming from all the different satellites. Meteosat, third generation example here, that is going back to the 60s, as early as the 60s, and the actually air quality measurements from satellite based. Who would hazard a guess were one of the first years that an air quality measurement was made from a satellite instrument? Guess, shout it out. 72. Yeah, that's a good start for the base, the land based. But then atmospheric spectroscopy. When did that start? Nope. Older, 78. And that's kind of fun because that's tied to my personal timeline, but I won't say why. I'm kidding. Yeah, so 1978, you have the TOMS, which was focused on ozone. And it's really interesting, as they developed the algorithm for ozone, they had to correct, and they were seeing features, and so the data products just started to expand. And because they had good spectral measurements, they could retrieve other products. So that's kind of the let's go on. Kind of one of my take-home messages today is that if I want to be an advocate for high quality, well-characterized spectral measurements, because you will always get more value for your money if you do a good spectral calibration, and you will always be able to discover new, either new molecules or new features or new aspects of the atmospheric composition that are important for a myriad of applications. So how does satellite data fit into the whole global air quality monitoring scheme? You may be familiar with, in this country from RIVM, the ground stations, and how, throughout the Western Europe and the United States, that there's this excellent coverage of hourly data sometimes with a higher time resolution of what the main pollutants are that are relevant for human health that are being monitored. But that's, of course, only one point of what we are measuring, because we are measuring an atmospheric column. And talked about cloud characterization. I also come up with a very different image in cloud. Clearing for clouds obviously is a major battle for trace gas retrievals. So it's Sentinel-2, of course, is a very interesting resource for us for if there's coincidence for extremely detailed information about cloud fields for specific types of studies. But yes, you can measure on aircraft, you can measure balloon-borne UAVs, but the backbone of our validation that is expanding greatly globally are these type of instruments that basically make a satellite retrieval but ground-based looking up. So they measure the atmospheric column, sometimes with profiling capabilities, so more information about the vertical distribution of a given trace gas. And we use that to compare our column measurements. So this is just a busy infographic, but we have a really enormous screen, so that's fine. You can see it all quite well for what our department does at KNMI. So I come from the R&D Satellite Observations Department, and we are busying ourselves with tasks that are summarized well on the right side of the panel here, involved in anywhere from the scientific requirements down to working with the engineers that do the instrument design, and then the calibration, so working in vacuum chambers, etc., to characterize the instrument on ground before it's launched, and then the full chain data processing and analysis. And we're involved in quite a few instruments at the time that this graphic was made. Our instrument just happened to be launched, so it got the prominent spot, but we're certainly not the only instrument, and I will talk a little bit about some of the interesting synergies of instruments that we are involved in. Oh, and can somebody start the clock, because otherwise I'm going to talk way too long. So yeah, so just to make sure you're not falling asleep before lunch, just the objectives of this talk. I hope that this talk will maybe trigger some things. You're all, most of you are like beginning career, and you will be involved with future satellite missions. And you might find yourself writing a proposal for a new mission, or on an instrument design review board, or indeed negotiating with some industrial or optical engineer about whether or not hardware meets scientific standards or the requirements that you need to meet with your data. And I just hope that you'll keep that in the back of your mind today with some of the things we'll talk about, and that you will just be able to also maybe incorporate in your hackathon the benefit of why we need high quality detailed spectral measurements for understanding atmospheric composition. So yeah, and I will, of course, biasedly use a Tropomi instrument, which I am involved with, as a prime example for this talk. So yeah, maybe you will find yourself working in these key elements at some point in your career, and I hope that this will stimulate your thoughts about that. So let's sort out some terminology, because in this world where it's all about jargon and alphabet soup, and and I hear the word, really the core idea of my talk came from the fact that I hear the word hyperspectral used often, and I would say that maybe what is truly, what is hyperspectral? What is truly hyperspectral? Is it multispectral? Is it multi-band? Are you actually just several panchromatic chunks? Resolution matters, and there's many kinds of resolution. So the spatial resolution we are extremely familiar with is smaller pixels, higher spatial resolution. Temporal resolution is revisit time. How often do you have a measurement? Radiometric resolution, how sensitive are you in the steps that you can measure of the intensity of your radiation? And then the spectral resolution, how fine are the slices along the wavelengths that you can actually say in a discrete way, what is my spectral resolution? So these are the things to keep in the back of your mind in my talk. And you can't have everything. I think that's also an important lesson for young career scientists. You can't have everything. Everything comes down to trade-offs. But there's always, of course, in our world, optimization. So think about, okay, is daily global coverage an absolute must for my instrument? Then you have to think bigger pixels. Then, you have to think, do I need absolutely tiny pixels? Then I have to sacrifice spectral resolution. Typically, that's one of the prime balancing factors. But I hope we can walk through a couple more of those comparison contrasts to get your brains thinking about other choices that are made and presented. Whenever you see proposals for new evaluations or new missions, because you can be the critical voice that says, is that really the best investment of our money? Do we really think we'll get the most benefit? Do we really think the error characterization is going to be good if we don't go for X, Y, Z in either radiometric or spectral resolution? Okay, so hyperspectral is very simple. First of all, I wanted to ask, who works with something that's categorized or described as a hyperspectral data or an instrument? Very good. Okay, I see some people out there. And so according to Merriam-Webster, obviously spectrum is light, comes from Latin. The second definition is more appropriate for us. We're not talking about ghosts. That's something very different, and that's not what they mean. But just the light. But I thought it was nice to just look at what their definition of hyper was, above and beyond. So you're, in a sense, oversampling so that you can ensure that you have a very high quality spectrum, because you want to be certain that that's what you're measuring and not some sort of interfering species. So just a quick text-heavy recap of some of the things we've talked about and seen already this morning. So surface imaging versus atmospheric spectroscopy. So we're all very familiar with Google Maps. It's just ubiquitous in our world, and generations since 1972, indeed. Landsat instruments have been running for more than 50 years. What an amazing resource. And atmospheric measurements also nearly that long. They're abundant. They're used for so many different applications. And the surface imager algorithms apply, of course, an atmospheric correction. So it's kind of the stuff that we're most interested is what we would glibly say is thrown away. But the surface imagers, of course, can use the primary component of the signal that's reflected or refracted off the surface. Atmospheric spectroscopy works more in the details, in the margins almost, as you would say, because it's operating on the principle of absorption. So we need to look at very tiny changes in the attenuation of that refracted radiation that's reaching our satellite instrument due to the presence of spectrally specific, spectrally dependent absorbing gases or aerosols, or other features. So this is just a generic cartoon showing that. So the more direct path of if you were just measuring surface reflectance and what is going on with the absorption and scattering, the complexity there, and how we characterize that with our retrievals. To give you a little insight into what that looks for some of the air quality and climate relevant species. You see down at the the wavelength along the bottom, and then just a generic depiction in the gray of the kind of the transparency of our atmosphere and some of the major components of that. So, of course, meteorology is really working on the water vapor. CO2 is a difficult retrieval for other reasons that I won't get into today. Oxygen, ozone are classic retrievals and kind of how our world started. Nitrogen oxides, especially in the Netherlands, are extremely important. And Rayleigh scattering tells us a little bit about especially UV absorbing aerosols and that fall off. So that's just a few examples of what the backbone is of the theory of what we're retrieving. And just again, to make a case for hyperspectral measurements, we're in a place today that we only started to imagine about 20 years ago. And what I mean by that is that our predecessor instrument, OMI, there were certain species like formaldehyde that took the entire mission average to retrieve. You needed that much data to even be able to see the signal. And now we are in this really excellent position that we can create daily images using of that same species of formaldehyde. We can create high quality daily images of methane, which is also something that was started, say, like in the Skiamaki years. And we just keep adding more exotic trace gases to the list, like glyoxal and nitrous acid. And so it's, I think, yeah, again, just to remind you that we're really working on the details of the light. This is just a really simple pie chart to remind you trace gases make up so little of the blue, overall blue pie here representing our entire atmosphere. And then of that tiny fraction, then, I mean, look at ozone, it's already, you know, it's 0.1, it's 0.01% of that already small fraction. So this is why we need really well calibrated instrument with high confidence in the spectrum that we're measuring. So it's all about trade-offs. We talked about this already a little bit about spatial versus spectral resolution, pixel size versus the amount of signal. So as you make your pixels smaller and smaller and smaller, you of course have less light making it to your satellite. And so you have to find that the balance between pixel size and amount of signal. And of course, the ability then to delineate the wavelength across that said pixel. So this is just go to the next. So I always like to think, to me, it's I love the idea of being at the drawing board kind of for a satellite instrument. And if imagine your budget would be unlimited, this is also fun for another type of hackathon. But usually we start in our world, we start with what species do we want to measure? Either because we have high uncertainty in global atmospheric chemical modeling, or there's a real interest from the health community or from biogeochemical cycling, or what do we need to know that we don't know well enough? What's limiting us in our modeling of how atmospheric chemistry is progressing? And how do we want to look at it? Do we want to look at it from a geostationary perspective, so a fixed area of the Earth, but then hourly, so the temporal resolution, your time resolution, or do we want to have a daily snapshot of the entire planet? Are we going to look directly down at the Earth? Or are we going to look at an angle to get more profile information, more vertical information? And will we do that with an active sensor or a passive sensor? Now, almost everything I show you today, of course, Tropomi is passive sensor, but we work together with really new just recently launched this year, EarthCare, which has all sort of interesting active sensors and is bringing the vertical distribution of aerosols and clouds in particular into really excellent detail. And also things like if you are going to have a detailed aerosol mission, how are you going to deal with polarization? There's all of these things, and all of these things, it comes down at the end when Ethan gives you the proposal in the ITT, the invitation to submit proposals. It comes down to budget timeliness and how well you meet your scientific requirements. And generally in our world, you say you may choose to. So yeah, it's like packing for a long flight. You can either pack completely, you can pack quickly, or you can pack lightly. You cannot do all three. And that's generally true for satellite instruments. So this is an older constellation, but it's set up and really worked as a model for many years for the atmospheric chemistry world, called the A-Train. So at the front of it is the predecessor for the instrument that I'm talking about. Actually, it's at the back. I'm sorry. The OMI instrument, which is a predecessor for the TROP-OMI instrument, and it's working together with a wide range of these sensors, all of those ones that I've just described. And so the potential for data synergy was really set up with this model. And I'll just walk you through a few of those. You can see the right in the middle, Calypso. This is the precursor to, whoops, yeah, no, that's not gonna work. There we go, there it is. So the precursor to the EarthCare mission that actually EarthCare kind of covers these two things, high detailed cloud information and with an active laser sensor that has better spectral resolution, and so lots more information about the vertical in great detail. You have then Aqua that's got the land surface imager and also lots of information about clouds and aerosols, and also OCO, which was really one of the early measurements of CO2 and carbon related cycling. And this was our atmospheric chemical platform for our instrument. So doing the total atmospheric column based on absorption. So yeah, all these things work together really well. Of course, you know, the imagers, they have the incredible spatial resolution, but then reduced spectral resolution. The active sensors are super highly detailed vertical information, but of course they can never have a broad swath. So they won't, their coverage of the planet is not wide. And then our instruments cover the spectra, but then of course with the lower many kilometer scale spatial resolution. So that's just kind of how, when you have the luxury position of working in a constellation, you get the maximum kind of observational benefit of the whole system. And this is shown always at many ESA conferences, and has already seen it this morning, but this just shows you the instruments that we're working on in our department, and some really interesting future instruments like CO2M, which I will touch on briefly later in the presentation. So again, I want to focus on TROP-OMI. So it's the tropospheric monitoring instrument. And of course, we continue the mission of monitoring the ozone layer. We are not fully recovered. I once spoke to a scientific speechwriter for a Dutch ministry, and she said, well, yeah, the Montreal Protocol was signed, so we don't have an ozone hole anymore. I said, oh, sorry? No, we are still monitoring it. We're still checking. There are signs of recovery, but of course, if you know the lifetime of all your chlorofluorocarbons, it takes time. So this is something in our fast-paced society and our fast-changing world. It's good to remember that satellites actually, especially these kind of what they're now calling backbone missions, really have a long-term view of our planet. And especially now that we have data that's approaching 50 years, we can actually talk about climatological change in the observation of atmospheric compositionally relevant components of our atmosphere. So yeah, then we really want to focus on what's happening in the troposphere. So getting closer to the information that's needed for modeling near surface chemistry. So the Tropomi measure was launched nearly 8 years ago. It has an afternoon overpass time, and all the data are available, but yeah, I think there's always a big asterisk there. How are they available? And I was glad that the czar conversation was raised this morning, because this is also something that we definitely are working with in our world and our data sets as well. Okay, so this is just to show you what that looks like, but this is nothing new to you, just that it's a ascending south to north orbit pass. So that gives you the idea that we need 15 orbits to get a daily global coverage. Okay, there we go. Yeah, so this is just a depiction of how that works, and just a simple cartoon visualization of how you have light coming into the sensor for a given a long track versus cross track position on the surface of the Earth, and that whole column that's associated with that spot. And then that light is broken up via grading, diffraction grading, into a spectrum, and is stored per that specific. So you really have, basically, if you picture X, Y, Z, you have your ground pixel space in 2 dimensions, and the wavelength in the 3rd dimension, and that's about 500 pieces of information that is stored per pixel per detector. And we'll do the breakdown of the math of exactly how that looks in the coming slides, but it's a lot of detailed information. So per scan line, for discrete positions across track, that spectral information is being gathered for all of the wavelength regions that we cover. And if you're interested in diving into the optics, with our instrument, there was a new technology called an immersed grading that actually made the shortwave infrared measurements possible in a really unique and new way. And I won't go into the details, but I just want to put a teaser out there for you hardware optical people. So you can think of it in a really high level sense that every species has its own unique absorption signature, and it operates kind of like a barcode in this way, in a very predictable way based on concentration. So this is what we are recording and analyzing to get to the species from our irradiance and radiance data. We have 4 detectors, as I mentioned. So that generic cartoon was for what would be for 1 detector, but that's happening in 4 detectors, starting from the UV, quite short, the high energy, to the longer wavelengths, where the classic components of tropospheric chemistry are coming from the UVs, and with Tropomi, the near and the sphere were new channels to our instrument. So it was really exciting to have methane being measured at this resolution. So this is actually a constructed image, just picking one of our level 1 engineers just picked 3 colors and combine them in an image, and of course it looks like this, but you can also see interesting features like sun glint showing up, near the tropics. You of course see all the clouds, and this was an image that was created for a first light event of when our satellite first started measuring and the instrument started measuring. And we asked, Andre Kaupers came to the reception and we said, so does it look like this? He said, well, I think you're a little heavy on the green because the Earth looks a lot more brown from space. We were kind of like, oh, bummer. But it's a pretty picture. But it's just to illustrate the point that we think in traditional camera sense of 3 colors, but Tropomi is measuring thousands, literally, with our spectra. And I'll just click to the next so you can see those spectra for the 4 detectors. And just to walk you through kind of the numbers of that that diagram I showed you. So you're starting from the ascending orbit. So starting from south to north, you're making scan lines, 1 per second. So that's in your cross track direction. And there's 440 spots along that scan line where those, all that remember in the Z direction into your page, so to speak, of the spectral information. So like 500 points, imagine, being stored roughly for each of those discrete across track positions. And then it takes 3,000 scan lines to cover the daylight ascending part of the orbit. So there's all sort of measurements that are happening on the night side of the Earth, but those are more for calibration and bookkeeping, etc. Housekeeping, sorry. It takes 14 orbits a day, which results in 20 million pixels per day, which I guess when you have 10 meter resolution, it sounds like nothing, but it's a lot of data. So of the irradiance and irradiance, there's roughly a terabyte of data per day. So again, we're not downloading this stuff. Okay, so what does spatial resolution kind of look like in comparison to its predecessors? When it was first designed, the box in the center, the T, represents what the planned, and for some products that need more signals, say like the UV and the sphere, have the 7 by 7 kilometer box. But we found that the signal and the performance was so good that we could reduce the pixel size for the UVN range down to 3.5 by 5.5. So in 2 years down in the mission, we were able to reduce the pixel size for even more clarity on ground. So for the first time, we could really truly look at variability within a city. So for the first time, we could see the difference between, say, the emissions from Rotterdam Harbor versus Rotterdam traffic. And this was very exciting. And this is an image that is just near and dear to all of our hearts because it was prepared for our first light event. So we weren't quite in operational phase yet, but we had a great image. So this is the morning measurement from the GOM instrument of SO2 over Indonesia because there was a volcanic eruption. And we're like, our instrument thankfully caught it, and this was the difference. So it just was such a visually game changer in the field of atmospheric chemistry to go from plume detection, you know there's a plume, to plume dynamics. So then you could actually see as an atmospheric chemical modeler, oh my goodness, that's really the plume shape. I can see turbulence. I can see the features that I know are acting on it and not just have an on-off switch, but actually intensities and shapes. Yes, go ahead. Yeah, so that's you can send commands. The characterization was such that you just change the timing of the instrument so that the kind of how I step through the scan lines, it comes purely down to when you're in what measurement mode. So it's the amount of time that we needed to collect those scan lines, and we could make that shorter. If I just go back, so where's the, oh, sorry. Yeah, so if you look at the bottom right, you can see there's a distance, and it's a dumb cartoon, but that distance is now shorter because you need less time to have the right amount of signal. Because previously we thought we needed more time, and so then you could actually reduce it because the things like dark current, noise were really low, and still are, thankfully, with the instrument. And it was, you know, it had to be a very a consensus to make that decision, because of course it makes a small step function in your data record, but everybody and all the modelers were like, dude, smaller pixels, yes please. So we had to take their time to make sure there would be no negative impacts, but once these settings were set, now they will never be changed again, as we hope. Okay, but good question. Yeah, and again, if anyone has a question, burning question like that, please do ask, because I think it's great. So yeah, so we went from plume detection to plume dynamics, and now, of course, there are so many different types of measurements of atmospheric chemical components. Either in a geo, we've got now this whole geostationary. I can, for the first time that I give this presentation, say that all 3 geostationary instruments have been launched and are operating. So this is really a new era that we're entering into. But Tropomi, because it has that optimization of the higher spatial resolution, again, not in comparison to Sentinel-2, but because of the spectral information at a relative, for us, higher spatial resolution, really maintains itself as a kind of operates like a base map to these different time overpasses and different spatial resolution and coverage instruments. And it's also becoming increasingly important for the developments in small commercial satellite world. But there is a but. We really are missing out on the global south. And this is something that has been raised in the broader satellite communities, that there really needs to be a push for some sort of geostationary instrument that's atmospheric chemically relevant, not just meteorological satellites, looking at the global south, because they are doubly limited, because there's almost no ground stations and there's no detailed information over the diurnal variation of chemistry. So I think the models really are missing out on full understanding of, say, like what's happening in increasing population in cities in African continent especially. So just to make a link, I've talked a lot about air quality, but the things, many species, species that are relevant for air quality also have a climatic impact. And just a couple of those, obviously methane, everyone is aware of methane and why it's so important to measure it, because its impact is very high, but its lifetime is shorter, which means it's actually easier for us to measure in a targeted way. And I'm gonna, in the sake of time, kind of walk through some of these examples a little bit quicker. But this is just a visualization of where the species are that we measure along the spectrum, and just keeping in mind that these things are both climate and air quality relevant. So I mentioned, I just want to put out a teaser for future missions that will be coming on. I think the planned launch is a little later than 2026, because that sounds really soon. I think it's been delayed by a year. We always say in our world, any good satellite is a delayed satellite. It's usually good for the on-ground calibration teams. They really need that extra time sometimes. But this is an exciting mission. It's been approved for 3 instruments. It has a more narrow swath width than we're used to, so it doesn't have daily global coverage, but because there's 3 instruments, it doesn't matter as much. And it's measuring it's CO2, methane, but also, I think, and this is really key, a very high resolution NO2, because NO2 gives you the capacity to see fossil-based plumes really readily, because its lifetime is only minutes, sometimes seconds, hours at the most. So you can really attribute it directly to a source, where that's very difficult for CO2, and less difficult but still challenging for methane. Because the longer something is in the atmosphere, the more readily it mixes with the background concentrations, and it's more difficult to separate it from point source emissions. And of course, if we're going to target climate emitters, climate relevant emitters, we need to know precisely where it's coming from. And this is another really cool, especially for the Netherlands, innovation piece. It takes 2 to tango. That's their tagline, and it's a really cool thing. So it's first measuring NO2 to have a heads up where are the fossil relevant plumes, and then thereafter you get the CO2 and the methane measurement. So they're happening in succession. They have really cool capacity for having a variable path. So if there's if it's coming up to a really interesting source that needs to be monitored, but it's just off track, it can go. It can like go around the corner to reach out for the plume of interest. So that will really enhance the revisit time for sources of interest. So this will be coming online soon. The contract was signed this year, so the clock is ticking very quickly, because in 3 years they will be launched and measuring. So this is also shifted by 1 year. And this is just an illustration of what that looked like in simulation from an airborne simulator. So this is a power plant field near Berlin. And you can start to see those individual stack plumes, which will again be a new game changer. And work really well with our data, because the algorithms are being developed to work harmoniously together. This is just a revisit of what we're looking at, and now is the tour de force pretty pictures time. I'm gonna shamelessly show you all of the exciting things that we can see from our instrument for all of these species, or at least most of them. So again, the core of our mission was started with ozone. So of course we're monitoring the ozone hole, Antarctic, but there's also developments of Arctic ozone holes as well. And so this has been a development that we've seen more often in recent years for the polar winters at both poles. So we monitor that. There's currently also tropospheric ozone retrieval that focuses on the tropics. And in addition to that, and I think my colleague is in the other room, but she's working on the ozone profile. So if you have any questions about the Tropomi ozone profile product, you make sure you reach out to Serena. But this is a really detailed information, especially can be used to confirm and for modeling capacity of better understanding ozone hole dynamics and transport. Sulfur dioxide. I have another colleague who is also working on that. Here's just to show you the contrast of big plumes, little plumes. We see quite a range of SO2 sources. So the smaller volcanic eruptions over Central and South America, and a larger eruption from Japan. They're all measured. You can see a progression. This was a really interesting, again, you go from plume detection to plume dynamics. We saw with Tropomi instrument for the first time these just incredible filaments of SO2 being transported all around the globe, and could monitor it for a really long time. Okay, good. And there's a newly upgraded SO2 algorithm. This is not the most exciting plot, but it's just to show you that the noise level went way down. And to illustrate that, I will show you these. This is an NO2 plot, so nitrogen dioxide that's coming from coal-fired power plants in India. And for now, with our new reprocessed SO2 algorithm, which has greatly driven down the noise, we can, for the first time, see the amount of sulfur that's also being emitted from these individual power plants that are using low-grade coal with high sulfur content. This would also be very true for the Highveld region of South Africa. So moving on to methane, there's a lot of attention for methane. This is a long time average plot to just show you that, yes, thermally, it's most methane is emitted in the tropics. Wetlands are extremely important source. So this zooms into that wetland area to show you in a detailed way what that looks like. Another one. And this is more work that's being done for understanding large methane emissions from landfills. So this is one that's in South America. And we work together with the private company, you probably have heard of it, GHGSat. It can also be used, we use the Tropomi data to trigger where there's an interesting plume, and then we can ask them to zoom in on plumes of interest, especially if they're leaks and things like what we're seeing here, persistent sources in Algeria. This is an example, but there have been many great examples of targeted, there's now an entire body that's under the head of UNEP to basically of public service to say, hey, your company is emitting methane, it's leaking, so please turn it off. If you don't turn it off, we will publish your data online. And it works really well. And at the end of the day, most oil and gas industries aren't crazy because it costs money when they have a leak. It has an economic disadvantage to them. So they want to know, and most of them will take the effort to turn it off. And we all know why. We need to also this is the global methane concentrations as measured from Tropomi. And this is a plot that I encourage my colleagues to show often, because you can't show it to enough policymakers, because we had to change the y-axis on this graph, unfortunately. So when we started out, we thought, oh yeah, it's not going to go above 2000. Look, the beginning of our measurement in 2018, April 2018. But sure enough, this is why our work is important. It shows very clearly in compelling way that our atmosphere is in trouble, and we are as a result. So yeah, this is led to the further development. So the International Methane Emissions Observation, our data is fed into that, and our colleagues at ESRON in the Netherlands, in Leiden, have created this really excellent service for these weekly, they create weekly maps of the key emitters for larger, medium to large sources across the globe. And this is a really excellent tool that is starting to get utilized more and more for control and mitigation. But NO2 definitely is a product that is still a little bit our favorite because it's such a rich data set. So this is 2 years averaged across the entire planet. So you can see a wide range of sources. And I'd say it's pretty convincing that fossil fuels matter. Any combustion of any kind results in NO2 emissions. So just people shout out, what do you see? Cities, absolutely. What else? Ships, yes. Isn't that exciting? You can really see the ship tracks, and it's not just in. I'll show you some more examples of those. What else do you see? What other tracks? Yeah, you can actually see, if you zoom in the summertime, you can see the highway that goes south to South France. It really shows up. And airplanes. You can also have a suggestion, of course, it's ships as well, but it's also the airplane tracks are really, people were quite skeptical in the beginning and were really, really testing, is this really, really, really what we're seeing? And it does really seem to be the case. So yeah, when you obviously sample tons of data for hotspots, persistent hotspots show up, and you can kind of, with this oversampling in time, have a even better spatial resolution. And that's what my colleague does on a regular basis, creates these regional, higher resolution 2x2 kilometer maps of persistent hotspots. Yeah, that's clear what's going on there. So this is just an example of ship length information superimposed on a ship track near the Strait of ship tracks in the Strait of Gibraltar. So this shows you that, in a way, you can actually take information to attribute the emissions to individual ships. And we're working with the Ministry for Transport in the Netherlands for better monitoring of this in the Rotterdam area as well, to see for compliance of fuel types. And this just is an example to show you that we don't just see the big cities like Rio de Janeiro and Sao Paulo over here on the right, but in the circle area, if you zoom in and change the color scale, sure enough, now we could for the first time see city footprints for increasingly smaller cities. And for those of you who are interested in the more ecological realm and land cover and plant productivity, there's this really interesting product called solar-induced fluorescence that that's measured in the near infrared channel, and this is an instantaneous measure of plant health and things like drought stress, and is a really I'd say extremely exciting and promising product because it relies on very little external a priori information, like say in comparison to NDVI, and it is really, I think, underutilized up to this point, especially in places like Africa, where things like tropospheric ozone that is being produced secondarily because of biomass burning that affects your plant productivity. So you can start to, with this very different product, start to disentangle some of those complex air quality, land cover cycle problems. And aerosol index is near and dear to my heart. It's the one I've worked on since my PhD research, and I still like to work with it. And this year we had some, there was really devastating fires in central Canada, and this led to some really spectacular plumes coming all the way to Europe. This plot just blows my mind. Of course, the scale, because of the projection, makes this blob quite large, but you just see the jet stream dynamics at work. You see it being deposited over Europe. You see the activation of the Sahara dust emission and in the Central Asian high plains. And this is just a little movie to show you what the smoke transport was like. I mean, sometimes, you know, the sunsets here were so hazy, and it's because it was Canadian smoke. We can see it being deposited over us. I'll let it go. Here it comes. There it goes. Okay. I'm going to skip this example, but the point is even large-scale fires can be seen with our data. This is from the imagers, but then in our aerosol index data, we saw an enhancement of, because this plume was above cloud. It was a really interesting case study. And just to wrap up with a few downstream applications of our data, if you combine it with information about transport, and you combine it with information about power plant productivity, you can use, you can first of all get excellent emissions of NOx, so nitrogen oxides in general, and you can also, if you know enough about the power plants and the characteristics of how they operate, you can create a very good proxy for the amount of CO2 that is being emitted by some of these top emitters. This is just to show you how well you can see when you plot the locations and the capacity of known power plants, how well you can see the individual plumes across, in this case, the South African highveld. And again, wrapping up, this data is being used in air quality forecasting. And in the last 10 years, this has been a really exciting field of development. It was quite rudimentary when I was starting my PhD, and now it's really getting more sophisticated. There's much more assimilation of this daily global atmospheric chemical information. And again, like I said, we're moving from just plume detection to plume dynamics, and this is really creating an excellent, I would say, positive knowledge feedback loop between the modelers and us, the measurers, because we can start to really drill down to process level studies to see what we're missing in the model, to know what we need to measure with future instruments. And I would say the air quality is just the beginning. I will leave this for your cogitation. I won't read it all, but I do want to encourage you to explore our tools for analysis and mapping. If there's ever a case study that you're interested in, whether it's smoke, whether it's dust, whether it's traffic, whether it's what you're interested in, I would encourage you to explore it. You can not just get snapshots. You can also look at the time series of the things I presented, like with the methane. It's all available. It's all online, and I would like to thank you for your attention. And I will leave up my funders as well. And I will leave up some of the critical links and the slides, which you all have access to, right? Eventually, will at some point. There is a full tutorial for data exploration if you would like to. It's very self-explanatory, so you can walk through of how you can access our data and play with the tools that I mentioned. So I will leave it there. Thank you very much.
Thank you so much, Deborah. Yes. Question? Yes.
Thank you so much for your insightful talk. And my question is, for as far as I know, at least for methane, the layer information is not enough to be trusted, and is not enough to be, like you, for example, used in the inversion study. Mm-hmm. So I was wondering, like, if this situation could be improved, like in the future, and in how far the future?
And so you're talking about tightening down emissions for individual sources or source types, or?
I'm talking about the layer informations, like we know that total chlorine
Yeah.
methane concentration is accurate, but like for each layer.
Layered.
Yeah.
So vertical. Yeah, I mean the averaging, there's averaging kernel information, of course, in the retrieval, but yeah, this is something that that needs to be improved. And I'm not the expert here, but there's been such excellent improvements in the validation and so many developments in the product that I would have confidence that they're working on it. So there was a lot of basically the approach for our team specifically has been to reduce known noisy areas. Like the last approach was to work on coastal sites, which are very important for the budgeting for, say, like the Delta regions that I showed you. So they've been really working hard with the new Copernicus digital elevation model, which is 90 meters. So for our pixels, this is a big deal. This is really improving the known sources, so that can help for the separation. So the more that they can separate the known sources, you can say more about the distribution and then the CAMS team, so the Copernicus Atmospheric Monitoring Service, they are doing more of the detailed level studies from a assimilation plus model perspective. So I think that's probably where the first answers are going to come, and there is a need for atmospheric chemical limb measurements as well. I think that's also part of the answer to the question.
Okay,
So,
thank you very
yeah.
much. And can I ask one? Thank you. Can I ask one? It's about when you using the high resolution data. When you pre-processing the data, you need a resample. Maybe you need resample them to the rougher resolutions. And
yeah.
And my question is like which resample method you recommend that can keep the total amount balance and the local features to maximum extent?
Yeah, that depends on the product.
Yeah.
And it depends on where are you resampling? Are you resampling radiances or are you resampling like trace gas concentrations?
Like the concentration.
Yeah. So that then the answer is definitely depends on the species, how you do that. Because NO2, for example, would definitely and methane even more would be predetermined by cloud. If cloud is anywhere, if you have multiple pieces of information, you always choose the one that's with the minimum cloud contamination. So this is also a question about sampling. I would love to talk to you offline about that.
Okay, thank you.
Because I think it's a long answer and it will take too long.
You. And also a very small issue. Like I noticed like one slide of your one slide you talking about the total methane chlorine, and I think the unit may be wrong.
Was it which?
The measurement buyer you talk about like the measurement buyer is less than 14 ppm, and I think it may be ppb rather than ppm. So
40 ppm. Oh Lord. Yeah, that would be bad. I'll check my slide. Thank you.
Hi, thanks for an excellent talk. You mentioned the global South and Africa and the lack of stations there. But I wondered, most of the relationships you kind of establish are physical relationships, right? So what is this? Is there some kind of local calibration going on? So why would you need these stations? If the physics kind of describes your calibration curve, you can apply it globally, right?
Yeah, of course
So what's so special about African cities?
Well, that they're growing very quickly, and the composition is very different than typical Western atmosphere. So we believe, and this was our experience in China especially, there's a low bias, we think, for the nose level pollution. We are less sensitive with most retrievals to the that nose level amount. So what really is, I think, something to find out what we don't know is really a step to have composition information on ground. Because if you would ask me, I think it's a different type of aerosol haze mix it's causing it to appear that there's less, say, NO2 present at nose level, or we're missing something with the tropospheric ozone cycling.
So your calibration curves are not global.
They're what?
They're not global. They're not constant.
For the radiance, of course. But for retrievals lean heavily on a priori information, which comes from chemical modeling. And when the chemical models don't accurately describe what's happening in a different chemical regime, I think we have unseen biases still.
Thanks. We have time for one last question before we break for lunch.
Yeah, also briefly to pick up on what his question was, also you have the standard latitudinal bias anyway, also for example for ozone, for example, in the stratosphere. But what I wanted to ask was for your tropospheric ozone, because before you said you use UV to measure ozone.
Mm-hmm.
How do you go down to the troposphere? Because I think those wavelengths you would go down to like 30 kilometers or something.
Yeah, so it's a broad spectral range, and yeah, the sensitivity indeed. Yeah, the shortest wavelengths are used for the ozone hole primarily, but the longer wavelengths are used indeed to get to the ground, and the ozone profile. I mean, literally, you can ask. She's in the other room. She's our primary developer specialist for the ozone profile, but it relies heavily on what is called a soft calibration. So it takes, again, a priori information from other limb sounding pieces of information to set it in the
like Sage or something, or
to train. Yeah. So, for example, from the OMPS instrument. So, short answer.
Thank you so much, Deborah. I encourage you, if you have way more questions, you will stay a bit longer.
I'm here
with
for the
us.
rest of the day. So.
Amazing. So just reach out to Deborah, but thank you so much.
And use the data. Make cool plots for your hackathon. I think you should get extra points if you add tropomi data, because I just think you should.
Thank you so much, Deborah. Okay, so we will break now for lunch. Those who will come here for the tutorial of Professor Etzer Pebesma right here on raster and vector data cubes in R and Python, we will see you here at 1:30. Thank you.